Welcome to Tech by Dr. Blood. This is the first of two videos related to sorting algorithms. However, we do need to cover some basic information before we can get too far along into that. So, here is the agenda. For this first video, we will just do a very quick refresher to Big O notation. Then we'll talk about searching, really just going to break it down between linear searching and binary search. And then we will talk about sorted versus unsorted data. The second video will jump right into sorting algorithms, where we'll use a deck of cards as well as some Python code to really break it down for you. Again, we're going to do the refresher. What is Big O notation? Well, it's an important concept when you're talking about algorithms. It uses math to describe the complexity of an algorithm. This is really important because you want to have standardization. You want to be able to compare apples to apples to determine how an algorithm is going to scale as you add more elements to it. So to do things get a little bit more complicated and take a little bit more time if you add additional items into the mix to be searched. Some will scale very nicely. We'll just add a small unit of measure to the results. Some will grow exponentially more complicated. So we like to use Big O notation because it does make it where we can have informed decisions. We can look at those true comparisons and say this algorithm appears to be more efficient for this scenario than a different one. And you really want to be able to do that. Some data sets are so small and today's computers are so fast that it may not make much difference, but you need to be thinking about as the information grows, as the data set gets bigger and bigger, are the computers going to be able to handle it in an efficient manner? You've hopefully seen this chart, or graphic rather. It's showing some of the common Big O notation measurements. Starting in the green at the bottom, your O of log n and O of 1, basically indicating that a search is going to be immediate. It takes just as long for the computer to give you the reading of the item at element 0 of an array as it does at element number 2,453. It's basically an instant amount of time. It's going to be the same no matter which one you're looking for. O of n indicates that you're going to grow 1 unit more complicated as you add additional items to the input set. So 100 elements is going to take a particular amount of time. Adding number 101 is going to take just 1 unit more of time. Seems kind of logical. However, as we go up into the chart and we look at O of n log n and O of n squared, we'll see that our time complexity gets much more complicated. And to explain that just a little through some text, I can tell you that if we have a particular set that we're working with 100 items, and it takes us 10 seconds to review the 100. It's an extremely slow computer, I guess. O of n would indicate that if we double the record set from 100 to 200, it's going to take just double the amount of time, just doubling the units of time. So now we went from 10 seconds to look at 100 elements to 20 seconds to look at 200. However, O of n squared says that it is going to get exponentially longer. So 10 seconds to look at 100 is now going to take 100 seconds to look at 200. And you see it gets even more complicated as you look at O of n factorial, which is kind of indicating that it's a poor algorithm and it may never actually complete. And now this brings us to linear versus binary searching, kind of two of our primary search techniques that we want to talk about. And linear search says that you're going to start at element 0. Remember, in arrays and computers, we generally start with element 0. So we're going to start at the location 0, and we're going to say, is this what we're looking for? Nope. Go to the next one. Nope. Go to the next one. We're just going to go right down the line, so linearly. And I have an example data set here on the screen. And I asked how many elements are examined when you're searching the following numbers. Well, when you look for your source of 6, you immediately get to element 0, and indeed that is the 6. So you've only searched the one spot. Well, how about 5? You looked at 6, 24, 16, 14, 5. It took, what, 6 tries to get to it. Okay, not bad. What about number 11? Well, 11, you see, is not in the list. So it had to go all the way through the list. Again, not a big deal here. We only have about a dozen. But what if this were a million, 10 million, a billion? You can see that that does not scale very well. It's certainly not going to be efficient as you have a large amount of data to go through. How about binary search? Binary search starts in the middle. If that's not the result that you're looking for, it's going to split it left and right. If it needs to go higher, you're going to look to the right, kind of find the next midpoint to the right. If it's lower, you're going to go to the left. And you just keep going, each time narrowing the results down by half. Binary search uses what's called the divide and conquer approach. Again, you're just kind of splitting your data in half repeatedly. We can talk about this on this current slide. Kind of goes back to the old game of I'm thinking of a number between 1 and 100. Now, you can do this in a couple different ways. You can just throw out numbers at random, but our binary search is going to suggest that you start in the middle. So 50. You can see on the screen it says no, the number is lower. So I'm going to say, all right, well, between 50 and 0, what's my middle? 25. Oh, the number is lower again. Okay, well, how about from 25 to 0? I'm going to split it again, 12. Now it says the number's higher. I'll split between 12 and 25. I've picked 18. It says the number's higher. I'm going to pick between 18 and 25. I've chosen 21. Congratulations, I guessed the number in 5 attempts. With linear search, how many tries would we have had to do? 1, 2, 3, 4, 5. We'd had to guess 21. So you see it's much more efficient. Again, this scales much better linear as you're going beyond 1 and 100. What if we'd gone 1,000? Imagine how many times you'd have to do it. So my question is, does binary search work for unsorted data? And the answer to that is no. It's not going to work. You have to have it in order already to be able to say it's going to be higher or lower. Otherwise, you're going to have numbers that are both higher and lower to the right, higher and lower to the left. So you have to have it sorted. So why sort data? Maybe we could have talked about this before. I wasn't sure how to order the slides. So we have to sort the data because without it, you're really going to have to rely on a linear search or maybe a random search where you're just picking this one, this one, this one, that one, trying to get it to work. It's very time consuming. O of n, if you go linearly, every guess, you're just taking another time, another guess. Sorted data, on the other hand, has many algorithms available, much faster. O of log n, for instance, and it's scalable for large data sets.